going to answer the assignment that I have assigned to you in the previous class, but as I've said, it will not be recorded. So I'm just going to show to you the process of solving this problem so that you can have guidance in terms of solving another problems, related problems in our class. Okay, so the problem tells us that you have a 0.750 kilograms mass which oscillates on an ideal spring, and the frequency of its oscillation is given to be 1.33 hertz. So the problem asks you for the frequency if 0.220 kilograms are added to the original mass, and when you subtract 0.220 kilograms from the original mass. So as I have said, we will start with the illustration of the problem. Okay, so let's illustrate the problem. So illustration. Just shift to a larger. Okay, so let's try to illustrate this problem. So you have a spring, say a spring, and then on the spring you connect a mass m. So let's denote that by m, and that m is found or is given to be 0.750 kilograms. Okay, and then the problem tells you that this is an ideal spring, and the frequency also is given to be 1.33 hertz. So 1.33 hertz, this is the frequency with which this mass that is connected on the spring, that is the frequency of its oscillation. So okay, so this is how we illustrate the problem, and then we will try to answer the frequency, since the problem asks us to find for the frequency if you actually add 0.220 kilograms and you subtract 0.220 kilograms. So there are two approaches to solving this problem that I have known. So the first one is to manually solve for the force constant K of the spring, and then the other is a more easier approach. So let's try to solve this first with the by finding the first force constant K. So that is our process of solving. We'll find first the force constant K of this spring. So of course not, it has a force constant K. So let's find that first. When you solve for that, uh, it would be easier if you will do it like this. So you will denote mass A. This is original mass plus the addition of 0.220 kilograms, and then you let or you denote m sub b to be the original mass m, and then you subtract 0.220 kilograms. Okay, so you have just put it here, 0.70750 kilograms. You add 0.220 kilograms. So let me just get my calculator. That would be 0.750 plus 0.220. So you will get 0.97 or 0.97 kilograms. We just That's mass A, and for mass B you will have 0.750 kilograms. You subtract 0.220 kilograms, and so you get, okay, this will be subtraction, oh sorry, okay, so you will get 0.53 kilograms. 0.53. So as I've said earlier, one approach of solving this problem is to find first the force constant K of the spring, and then you go on with the equations that you know. But I will show to you first the equations that we are going to use here. So I think you remember in the class, equations. I think you remember this in the class that the frequency is just the inverse of the period, right? So the frequency is just the inverse of the period. So let's label that as equation 1. Equation 2 is the angular frequency omega. You have angular frequency omega, and that is just angular part, the 2 pi, frequency f. Okay, so that's 2 pi f. Let's put it, let's label that as equation 2. Okay, so as I will be showing to you two ways of solving this problem. The first one, which we are showing right now, is the longer way of doing it, and the other one is a more clever and easier way of doing it. So from these two equations, let's try to work out an expression for what's this? An expression for frequency that involves, if you notice, if you're going to use the first equation, you could not just simply do it. I mean, you could not just simply use this because you don't have the period t, right? So that's pointless if you will automatically use this second equation. For the second equation, um, you cannot also use this one because you do not know yet omega, okay? But remember in the previous discussion where we relate the, I'm hoping you can remember, where we relate the circular motion and then the periodic motion, we have found out that the value of omega is actually equal to the square root of the force constant K divided by the mass. Okay, so the K is, again, this is the force constant of the spring with which your mass is attached, and then this mass here is the mass not of the spring, because we assume the spring to be massless, but this is the mass of the one being attached to the spring, mass of the attached body. Okay, so this time let me just call this one equation 3. Therefore, our goal, as I've said, the first thing is we need to find for K, this force constant, right? But if we are going to use equation 3 to find for the force constant K, we cannot directly use that because we don't know omega, right? So what we are going to do is to try to manipulate this equation. So let me just change the color. So I'll put it here, manipulating equations. Okay, so this usually happens in a lot of physics problem. You actually have to manipulate equations. So here, what you are seeing here, class, is that you can actually manipulate this equation here and this equation, meaning we will be working with equation 2 and equation 3. So what that means is that since omega is equal to 2 pi f, that's what equation 2 is telling us. Equation 3 is telling us that omega is equal to the square root of k over m. So just like saying that, it's just like saying A is equal to B. I don't know if you're familiar with this one, or if you can remember this one. And you have A is equal to C. So as a consequence, this implies then that what? That B is equal to C. Okay, so that is what we are going to do in this equation here. So we have 2 pi f is simply equal to the square root of k all over m. Okay, so as I have said, this is the long way of doing it. We need to find for the force constant K of the spring first. So that means that in order to get rid of this radical sign here, we have to square both sides. Okay, square that, Then you square this part also, so you are left with 4 pi squared f squared is equal to um what's this? It's equal to, okay, the square root will cancel out, so you have k all over m. So let me just simplify this one. As I've said, this is the long way of doing it. Okay, so we will show later a more clever way of doing this problem. So 4 pi squared f squared, of course, you have now the mass here is equal to k. So what happens is basically you multiply both sides by mass m, such that the mass m on this portion here will cancel out. Okay, so you now have an expression for k, this one. So what you are going to do next is simply to plug in the values. So from this one, you'll have k is equal to 4. Of course, pi is simply a constant squared. And then the frequency is the one given in the problem, that is 1.33 hertz. Okay, 1.33 hertz. And you square that. So you have the k, the force constant, is given to be, okay, let me just check. Oh, we forgot the mass m. Okay, the mass m is originally 0.750 kilograms, so 0.750 kj, sorry. Okay, so here in this part, you'll just have to plug it in the calculator. So this is a constant. So hertz again is just, this is simply um like 1 per second. So we'll just checking if the units does make sense. So yeah, so you will get kilogram, so expected to get kilogram per second squared, which is you will see later in the class that is just equal to the Newton over meter. Newton over meter, this is the unit, SI unit for the force constant K, and that is equivalent to kilograms per second squared. Okay, so let me just work with my calculator. 4 pi squared, you multiply it by 1.33 and then you square, and then the mass, you plug in the mass, 0.750 kilograms. Okay, so you will get the force constant K to be, I will round it off to the two decimal places, so that's 52.38. Okay, kilograms per second squared. So that is your force constant K. Well, I am bothered if you will not believe me on how these two terms are equal, so I will just show it up to you right now. So 1 Newton is 1 kilogram meters per second squared. So divided by meters here. So let's see what will happen. So the meters will cancel out, so you are left with kilograms per second squared. Okay, so yeah, Newton per meter is simply kilogram per second squared if you try to simplify it. Okay, so let me you need to remember that the force constant K is 52.38. Now, since the problem asks us to find for, if you can see, the problem asks you to find for the frequency if you add 0.20 kilograms, meaning you have 0.97 kilograms. And it also asks you to find for the frequency if you subtract 0.220, or the mass that is attached now is, after subtracting, that's 0.53 kilograms, right? So we will work with that right now. So the equations, of course, that we are going to use is still will still manipulate equation 2 and equation 3. Okay, so let me just move on to the other page. Okay, so according to equation 2, the omega is equal to, oh, I like this one, mas ano siya baga, 2 pi f, and another one is omega is just equal to the square root of k over m. Okay, so our goal here is to find for f. So we can still equate that, since they are practically equal. 2 pi f is equal to the square root of k over m. So this time around, we don't need to the square both sides because our concern here is f. Okay, so squaring both sides will simply it will just complicate things. Okay, so what you're going to do then is you multiply both sides of the equation by 1 over 2 pi. So that leads to the cancellation of this 2 pi here. So you are left then with that the frequency is simply you have, okay, 1 over 2 pi multiplied by the square root of k all over m. Okay, now for a, this is where you add the 0.220 kilograms. So we have solved that earlier, so that is the mass referring to 0.97 kilograms. Okay, so the mass is 0.97 kilograms. Okay, so from this one, by the way, we'll just put here the k. We have solved earlier the k, right? The k is just I forgot, it's 52.38. That is kilograms per second squared. Okay, so the frequency will have this one 1 over 2 pi. Just plug in the values, and 52.38 kilograms per second squared. So I encourage to always put the units just as a measure of just to make sure that you are actually arriving with the right unit. So it's one way of checking if you got it right. So for the mass, this is now 0.97 kilograms since we added already the 0.220 kilograms. So as you can see here, the mass would cancel out. I mean, the kilogram units would cancel out. So you have the frequency. Let me just work with my calculator. So 1 over 2 pi, and then you have the square root of 52.38 divided by 0.97. So that is 1 point, you have frequency of 1.17. Now the question is, of course, when I will just show what happens on the unit here, in the radicand. So you have what happens is 1 over second squared. So what happens is, okay, so you have squared, so the second will just come out. So you have 1 over second. So the unit that you have here is 1 over second, which we know to be hertz, right? So that means that it's 1.17 hertz. So this time you are sure that at least you are dealing with the correct variable since you arrive at a correct unit for frequency, which should be in hertz. Okay, so the same thing happens with part B. So let me just write part B here. Okay, so for part B, the mass is now, I forgot, the mass is at 0.53 kilograms. So 0.53 kilograms. Okay, so we'll just plug in the values. So you have 1 over 2 pi of the square root of 52.38 kilograms per second squared, and you divide that by the mass, which you subtracted already. So you have 0.53 kilograms. So you see, these kilogram units would cancel out. So you are left with, basically, this is the same with A. You just change the mass. Okay, so you have 0.58. Okay, so you have, from the calculator, it displays 1.51. So 1.51 hertz. So this is now the new frequency. So this is the frequency when you added a certain mass, and this is the frequency when you reduce the mass. So what are your observations? So this is lesser, right? So the frequency, let me just put it here. The frequency on the bigger mass is lesser compared to the frequency of the smaller mass. Okay, that's how I denote it. So you'll find the explanation for this one. Probably in the class I will ask you why is that, does that make sense? Okay, so that is the long way of doing this. There is a clever way of doing this one and I will show it to you shortly. I will be showing to you, as I've said earlier, the easier way of doing this one. So I just wrote here the masses. So mass A is when you already add the 0.220 kilograms, and mass B is the one with which you deduct the 0.53 kilograms. Now, the first thing that you need to realize is that if I'm going to draw the cases here, I will say A, in which you now have MA, meaning this is where you have additional mass on the spring, and then you're working on the same spring, and then you have massive B. What you need to realize is that when you have the original mass M, it oscillates at a certain frequency, right? But that spring still has the force constant K, which we have solved to be somewhere around 52 earlier, right? So when you have an additional mass, in this case that is MA, which is 0.97 kilograms, you must realize that the force constant K is still the same, regardless of the additional mass that you have. And so is what the case when you deduct another mass or mass of B. So that's one of the things that you need to realize. The force constant K doesn't change in these cases. So that is why your technique would be not to solve explicitly for K anymore, but you can actually equate the K's. You equate the expression for K of this one and this one, and so you can work also with this one and this one. So in that way you will not really solve for the value of K, but you simplify your solution. So let me show it to you. Okay, so for the case of the original mass here, let's change the size. Okay, for the case of the original mass, you have of course, you will still be dealing with omega is equal to 2 pi f, and then another equation would be omega is equal to the square root of k over m. So this time we are going to find for expression of k. Okay, an expression of k. So that means that you will have 2 pi f is equal to the square root of k over m. So how do you find for k? Of course, you have no other way but to square both sides. So squaring both sides, you have 4 pi squared frequency squared is equal to k all over m. So the radical sign is now removed. So you have 4 pi f squared k all over m. Okay, just for you not to be confused, let me put it here with the big capital letter M. So I am referring to the original mass where you don't have deduction or addition. Okay, sorry, so this should be put here. So should be k is equal to 4 pi squared, I forgot the squared, f squared times mass m. Okay, so this is your first equation. So the second equation is, I will not go through that because basically this is the case where you add the mass m sub a, or you add the mass, 0.220 kilograms. So your new mass now is m sub a, or 0.97 kilograms. So you still go through with the same process here. You work with the same variables except for the mass m. Okay, in this case, your expression for k, after going through the same process, so you go through the same process. So your expression for k would be 4 pi squared, you have f squared, let me just correct it later, and then your m here is no longer m, the original mass, but m sub a. And I should also make it a point here, do not repeat what I have committed here. For next time, you should denote it as f sub m, meaning this is the frequency of the original mass. So and so is this one, f sub m, f sub m, this is f sub m. Okay, so f sub m. So in our new equation for the case 2, where you add 0.220 kilograms, so the f there is different from f sub m, so it should be f of m sub a, meaning this is now the frequency of the oscillation when you actually added a new mass that is 0.220 kilograms. You add 0.220 kilograms, so you have 0.97 kilograms. So that's one of the things that you need to be careful of next time when you will be solving. In fact, I have committed that mistake here. The good thing is I was able to spot that, oh my god, this is going and all. So since you have these expressions, so you have k is equal to this one and k is equal to this one. So what is, you can just equate that since k is equal to k, or I think I'm nagbulol ko dari class. So what I mean is, if you remember in your math, if you have a is equal to b and so is a equal to c, then this implies that B is equal to C. So this is what happens here. So I think that is a transitive property. So you will be dealing with I find blue uncomfortable in my eyes. So I think I'll go with black. So you equate that, you have 4 pi squared f of m a squared multiplied by m sub a, and then you equate it with this term. Oh, this is looking good. 4 pi squared f m, so for the original mass, squared times m. Okay, so since 4 pi squared is common both sides, so that means it will simplify our problems. So you cancel that out since those are common terms. So you are left with a simpler equation now. You have f of m sub a, so f squared, and then you have m sub a is equal to f of m, meaning the original mass, squared m. Okay, so since we are going to find for the frequency where you add already the mass, so you retain it here on the left hand side of the equation, f of m sub a, you square that, and then you have f of m squared m. So this a here will be put here, you simply divide that, so you have m sub a. Okay, so you're dealing with squares. So the nice thing to do here is you take the square both sides. So taking the square both sides, so that will simplify our expression. So that's the radical will be taken out. And so is the case for the f sub m, but only in the f sub m will be simplified. Okay, so what happens here then is you have f of m sub a, meaning the frequency of where you already add the mass, is equal to, of course, this will, the radical sign on the first term, that will simplify, so you have f of m, and then you are left with the square root of m all over m sub a. Now the first question that will arise is, do I know f sub m? Yes, you do know this because this is given in the problem. So that is 1.33 hertz, because f sub m is the frequency of the original mass, and so is m. This is the mass of the original mass. The m sub a is where you added 0.220 kilograms, or that is 0.97 kilograms. So you see, this is a simpler way of doing things, because fm sub a is now the frequency of the mass with which you added 0.20 kilograms. So what happens is you simply plug in the value, f of m sub a is equal to f sub m, is that is 1.33 hertz, and then you have the square root of m, which is 0.750 kilograms, divided by m sub a, the one with you add 0.220, so that is 0.97 kilograms. So you see that the kilograms will cancel out, so you are left with hertz, which is a good sign that you are in the right direction because you arrive with the correct unit. So let me just work with my calculator here. So 1.33, the square root of 0.750, 0.97. So you have 1.17. So you are getting 1.17 hertz. And I think you can verify that this answer that we have arrived matches the one we have solved earlier. Where is it? Okay, 1.17. But this time, this is easier and more compact to do. Now, for the second term is uh, it's just that you still work with the same process. You still work with the same equation, but okay, I'll just show it to you so that it will not be very abstract for you. Okay, this final equation that you have here, you still going to arrive at that the same equation. I think I should put it in red. So you have f m sub a is equal to f of m, the square root of m over m sub a. Okay, so but this time around, since you are asking for the case b, meaning the case in which you deducted point how much was it, 0.220 kilograms. So the same process that you are going to do with this one, you express omega and find for k. But this time around, when you work through this, I'll put it in square. When you work through this process here, the one I put it in square, the only difference that you would get is this one, the unit, I mean the variables. So you will find that k is equal to 4 pi squared. Instead of having f m sub a, you will get f of m sub b squared m sub b. Okay, so you work through the same process. Actually, you work through the same process, which I will not show to you because it's very clear how you go about with that, and to save time also. So what will happen to your equation now is you will have f of, instead of m sub a, f of m sub b is equal to the same thing here, f sub m, the square root of the m, all over, instead of m sub a, that will be m sub b. So that's basically just this case here and this case. You consider the two cases. Okay, so this is now easy to manipulate because I mean you simply have to plug in the values. For example, f sub m, this is the original frequency of the original mass, that is 1.33 hertz. And then you have the square root of the original mass, which is 0.70750 kilograms, and then you divide it by mass b, so meaning the lesser mass where you deducted 0.220 kilograms, and that is 0.53 kilograms. Okay, so you see that the kilogram units will cancel out, so your f of the mass of b is equal to, let me work on my calculator, 0.53. Okay, so you will get 1.58. So 1.58 hertz. Okay, so let us verify if the one that we have solved, 1.58 hertz, is the same with the previous process where we solved for k first. So okay, so this is the case A, the case B. Oh, so we have a short disparity of the value. So we have different values class. So let me just check it back in my calculator because it's possible. I believe I'm 100% possible. I'm 100% positive that I just plug in a wrong value in my calculator. So let me just redo the input here. So 1 over 2 pi square root of 52.38 divided by 0.53. Oh, here we go. So that's 1.58. So I did just have the mistake class of plugging in the values in my calculator. So that's 1.5822, so 1.58 hertz. So you see, um, you have two different processes shown. First one is quite lengthy, and the first one is practical because it's easier to follow. So that's up to you how you do the problem. So that's the beauty of doing physics. You have different way of dealing with the problems and getting the same answer. So I think this will be all for your assignment. I'm hoping you understand it. And if you do have any question, please do not hesitate to email me on my consultation hours. So that's it. I'm hoping you learned something. So I think that's it. So sayonara, everyone.